Hi everyone, in this recording we'll be going over vectors in the plane. Our goal is that by the end of this presentation you'll be able to represent vectors as directed line segments, you'll be able to write vectors in their component forms, you'll be able to perform and represent vector operations graphically, and you'll be able to write vectors as linear combinations of unit vectors. Force and velocity are quantities that involve both magnitude and direction and cannot be completely characterized by a single real number. So the directed line segment represents such quantity. So the directed line segment PQ has initial point P and terminal point Q. Its magnitude, or length, is denoted by the norm of the directed line segment PQ and can be found using the distance formula. So if we have two directed line segments that have the same magnitude, they are equivalent. Vectors are denoted by lowercase bold-faced letters, for example, U, V, and W. The component form of a vector v can be written as v is equal to v1, v2, where v1 is the horizontal component parallel to the x-axis and v2 is the vertical component parallel to the y-axis. So the component form of a vector with the initial point p and terminal point q is given by, now the horizontal component is the difference between the last and the first point, so q1 minus p1 in the horizontal portion, and the vertical component is given by the difference between the last and the first point in the vertical portion, so q2 minus p2, and that'll give us v1, v2. Now the magnitude or the length of v is given by the square root of q1 minus p1 squared plus q2 minus p2 squared, or just taking the square root of the sum of the squares of the components. So squaring each component, adding them, and then taking the square root of the final sum. In this example, we are told to show that the vectors u and v are equivalent on the plane. So in order to do so, we need to show that they have the same magnitude, and we will use the distance formula to do so. So first, we label our terminal and our initial points for each of the vectors. So the vector v has an initial point of 2, 3, and a terminal point of 6, 0. So I labeled our P1 and our P2 for our initial, and our Q1 and our Q2 for our terminal. And then we have the formula, so we just plug in Q1, which was 6, and P1, which was 2, so 6 minus 2 squared, plus our Q2, which was 0, minus our P2, which is 3, so 0 minus 3 squared. So we'll have negative 3 squared plus 4 squared. Now 4 squared is 16, and negative 3 squared is positive 9, so 16 plus 9 is equal to 25, so we'll take the square root of 25, and that'll give us 5. Now repeating the process for our vector u, we label our p1 and our p2 and our q1 and our q2. So for our q1, we had 4, and p1 is 0, so 4 minus 0 squared, plus now our q2 is negative 3 minus 0, so that'll give us negative 3 squared. So 4 squared, 16 plus negative 3 squared, 9. So 16 plus 9 is equal to 25, and the square root of 25 is equal to 5. So both our vectors have the same magnitude, and therefore they are equivalent on the plane. In this portion, we are told to find the component form and the magnitude of the vector v that has the initial point 6, negative 16, and the terminal point negative 4, 8. So first we can start by labeling. So our initial point 6, negative 16 will be labeled P1, P2, and our terminal point negative 4, 8 will be Q1, Q2. So for the horizontal component, we take the difference of the x coordinates, so the final x coordinate in the initial one. So we have Q1 minus P1, so negative 4 minus 6, and that is equal to negative 10. We do the same thing for the horizontal component. So we do Q2 minus P2, so 8 minus negative 16, so that'll be 8 plus 16, and that'll give us 24. So in component form, our vector v is negative 10, 24. Now to find the magnitude, we square each of the components, we add them, and then we take the square root. So we have the square root of negative 10 squared plus 24 squared, and that'll give us 26. There are two basic vector operations, scalar multiplication and vector addition. So scalar multiplication is the product of any real number represented by k times the vector v. So we just multiply each of the components of the vector by k. Now for vector addition, this is the sum of two vectors u plus v, And this sum is formed by joining the final point of the vector u with the initial point of the vector v. Now, if we let u, v, and w be vectors and c and d be scalars, then the following properties hold. So for the first one, u plus v is equal to v plus u, so the commutative property of addition. The second one, in parentheses, u plus v plus w is equal to u plus, in parentheses, v plus w. This is the associative property of addition. For the third property, u plus 0 is equal to u. This is the additive identity. Now for the fourth property, u plus minus u or negative u is equal to 0. So this is the additive inverse. Now for number 5, c times, in parentheses, d times u is equal to c times d, and then in parentheses u. Now this is the associative property for scalar multiplication. Now for number 6, we have in parentheses c plus d times u, and that is equal to c times u plus d times u. And this is the distributive property of scalars over vectors. For number 7, we have c times, and then in parentheses, u plus v, and that is equal to c times u plus c times v, and that is also the distributive property of scalars over vectors. Now for number 8, we have 1 times u is equal to u, and that is the multiplicative identity. Then we have 0 times u is equal to 0, and that is the zero property of multiplication. And lastly, for number 9, we have the magnitude of c times the vector v is equal to the absolute value of c times the magnitude of v. Now here are examples to practice the vector operations. So first we're given the vector -4, 10, and the vector w, 6, 8. So we need to find each vector. So for part A, we have 2 times v. So that means we would multiply each component of v times the scalar 2. So we'll have 2 times -4, 2 times 10, and that'll give us -8, 20 as the vector for 2v. Now for part B, we're supposed to subtract the vector v from the vector w. So we can set up our two vectors, and we will subtract each of the components. So for vector w, we have 6, 8, and we'll be subtracting from that vector for -4, 10. So we will do it component-wise, so 6 minus -4, and 8 minus 10. So that'll give us 10, 2 for the vector for w minus v. Now for the last portion, we have v plus 2 times w. So we're doing vector addition, and we're doing multiplication, scalar multiplication for w. So we'll multiply 2 times each component in w. So it'll be 2 times 6 and 2 times 8, so that'll give us a new vector of 12, 16. Now we can add that to our vector v. So component-wise, we'll do -4 plus 12 and 10 plus 16. So -4 plus 12 gives us +8, and 10 plus 16 will give us 26. So now our new vector for v plus 2w is 8, 26. In these examples, we'll be practicing finding the magnitude for a scalar multiple. So we need to recall that the magnitude of a scalar times a vector is equal to the absolute value of the scalar times the vector. So for example A, we have to find the magnitude of 2 times the vector u. So that'll be the absolute value of 2 times the magnitude of u, and then we find the magnitude of u by squaring each of its components, adding them, and then taking the square root of the final sum. So for the vector u, we have the components 2 and 6, so we'll do 2 squared plus 6 squared, and we take the square root of that. So 2 squared gives us 4, and 6 squared gives us 36. So we have 4 plus 36 under the square root, so 4 plus 36 will give us 40. Now 2 factors of 40 will give us 4 and 10, so we could do the square root of 4 times the square root of 10. And the square root of 4 is 2, so we'll have 2, and then the square root of 10 will not give us a perfect square, it'll give us a decimal, so we can just leave it in that term. So now we can plug that in to right here. So we had the absolute value of 2, which is just 2, times the magnitude of the vector u, and we just found that right here, so we can plug that in. And that is how we get this final answer right here. 2 times 2 is 4, and then we leave the square root of 10. So that is the answer for part A, to find the magnitude of 2 times the vector u. So now for part B, we have to find the magnitude of -5 times the vector u. So we do the absolute value of -5, so that'll be +5 times the magnitude of vector u. And previously, for example, A, we had already found the magnitude. It was 2 times the square root of 10. So now we can plug that in, and we'll have 5 times 2 times the square root of 10. Now 5 times 2 gives us 10, and then times the square root of 10, and that is how we got the answer for part B. Now part C is the same concept or the same steps, but now we have to do the vector v, and I will leave that one as practice for you. A unit vector is a vector with a magnitude or a length of exactly 1. So if u is a scalar multiple of v, then the vector u has a magnitude of 1, and it is in the same direction of v. So the vector u is called a unit vector in the direction of v. And to find the unit vector when it is not normalized, we can plug it into this formula. So it'll be v, the vector v, divided by the magnitude of v, and that is how we get the unit vector u. And normalizing just means scaling down a vector so that it will have a length or a magnitude of 1. So here we're given the example. We're told to find the unit vector u given the vector v. So v has components 3, 4. So first we need to find the norm of v, so that will be equal to the square root of 3 squared plus 4 squared. So we square each of the components, add them, and we take the square root. So 3 squared is equal to 9 plus 4 squared, that is equal to 16. So 9 plus 16 is equal to 25. So the square root of 25 is equal to 5. Now we multiply by 1 over 5 by each of the entries in vector v, or we just divide by 5. So we'll do 3 divided by 5 and 4 divided by 5, and that'll be our normalized vector, 3 over 5, 4 over 5. And we can double check that this vector has a length of 1 by taking the magnitude. So we take the square root, and then we square each of the components and add them. So we'll have 3 over 5 squared plus 4 over 5 squared. So 3 over 5 squared is equal to 9 over 25, and 4 over 5 squared is equal to 16 over 25. Now inside the square root, we have 9 over 25 plus 16 over 25, and that is equal to 25 over 25, and that is equal to the square root of 1, and the square root of 1 is equal to 1, so that means our work is correct. Now here we'll be finding the unit vector of v is equal to 5, 12. So first we need to find the magnitude of the vector v. So we square each of its components, add them, and take the square root of the sum. So the components of the vector v are 5 and 12. So 5 squared plus 12 squared, that'll give us 169. Now the square root of 169 is equal to 13. Now we normalize the vector v. So we multiply each of the components in the vector v by 1 over the magnitude, so 1 over 13. So we'll have 5 over 13, 12 over 13. Now lastly, we verify that this new vector u has a length of 1, so we take the magnitude of the new vector, so we square each of the components, so 5 over 13 squared plus 12 over 13 squared, and that'll give us the square root of 169 over 169, and that is equal to the square root of 1, and the square root of 1 is equal to 1, so that means our solution is correct. Direction angles are the 3 angles that are non-zero vector in a 3-dimensional Cartesian plane coordinate system that make the positive x, y, and z axes. So if u is a unit vector such that theta is the angle from the positive x-axis to u, then the terminal point of u lies on the unit circle, and you have that the vector u with the components x and y has equivalent components cosine of theta and sine of theta. So x is equal to cosine of theta, and y is equal to sine of theta. Now here we have these I and j's. So that means that any vector u can be written in the linear combination of our x component times the unit vector I plus the y component times the unit vector j. So I is the standard unit vector in the horizontal direction, and j is the standard unit vector in the vertical direction. So for example, if we're given the vector u has components 4, 3, then that is the same thing as saying u is equal to 4 times I plus 3 times j. And that is the same thing as doing 4 times the I unit vector plus 3 times the j unit vector. So 0, 1. So 4 times 1, 0 is 4, 0, and 3 times 0, 1 is 0, 3. So then we can add the two vectors. And then adding each of the components, 4 plus 0 gives us 4, and 0 plus 3 gives us 3. And that is the vector that we started off with. So now going back, we have that the vector u with components x, y has components cosine of theta, sine of theta, where x is equal to cosine of theta, and y is equal to sine of theta. And we can write that in the linear combination form of cosine of theta times our unit vector I plus sine of theta times our unit vector j. So looking at the figure to the left-hand side, we have the angle theta, and that is the direction angle of the vector u. And we have the x component is equal to cosine of that angle theta, and our y component is equal to sine of theta, the direction angle. So if we're given any vector v, and we write it in its linear combination form, a times I plus b times j, where a and b are each of the components multiplied by the unit vectors for each direction, so I, the horizontal component, and j, the vertical. Then we can also write v as the magnitude of v times the cosine of theta in the I direction plus the magnitude of v times the sine of theta in the j direction. So because v is equal to, in its linear combination form, a times I plus b times j, and that is equal to the magnitude of v times the cosine of theta times our horizontal component, or our horizontal unit vector, plus the magnitude of v times sine of theta times the vertical unit vector j. It follows that the direction angle theta for v is determined from the tangent of theta, and we recall that our vector v in component form was just a, b, and we stated a was equal to the cosine of theta and b was equal to the sine of theta. So now, using the quotient identity, where the tangent of theta is equal to sine of theta divided by cosine of theta, now we can just multiply it by the magnitude of v on both the numerator and the denominator, and those cancel out, and we just get sine of theta divided by cosine of theta. Now, plugging back in a and b, we get the sine of theta is equal to b, and the cosine of theta is equal to a, so we just have b over a. So the tangent of theta is equal to b over a. Here we're given a force of 1,200 pounds is required to pull a boat and a trailer up a ramp inclined at 15 degrees from the horizontal. So here's the horizontal, and the ramp is right here, and it is at an incline of 15 degrees. We are told to find the combined weight of the boat and the trailer, so we can construct vectors from these initial and terminal points. So for the force of gravity, that is the combined weight of the boat and the trailer, we will form this vector right here, initial point B and terminal point A, and that force will be given to us by the magnitude of that vector. Now the force against the ramp is given by this vector, the initial point B and terminal point C. Now the force required to move the boat up the ramp was given to us, 1,200 pounds, and that is the magnitude of this vector, initial point A and terminal point C. So since AC is parallel to the ramp right here, we will have similar triangles. So BWD, this triangle right here, that triangle in the yellow, and then ABC right here, they're similar. So that means that the angle right here will also be 15 degrees. So relabeling the triangle, or redrawing the triangle and making it bigger so it's easier to see what we're looking for, we're given this angle right here, the sine of 15 degrees, and then I will write each of the corresponding magnitudes. So right here we have the magnitude of AC, right here we have the magnitude CB, right here magnitude AB. So we are looking for the force of gravity, or this magnitude right here. So since we're given the 15 degrees, we can use the sine of 15 degrees. So we know sine is equal to opposite over hypotenuse. So the side opposite to this angle is AC, and then the hypotenuse is our force of gravity, so AB. And that's how we get this first step right here. So now we were given the magnitude of AC, so that was 1,200 pounds, so we can plug that in here. And now we can solve for the force of gravity. So we multiply by the magnitude of BA on both sides to cancel on the right hand side. Then we can divide by the sine of 15 degrees to isolate the magnitude of BA. And we get that BA is equal to approximately 4,636 pounds.